What do you see when you look up at the night sky? Well, if you live in a big city, probably not much. But if you go someplace very dark, you should be able to see thousands of bright stars. In the summer in the northern hemisphere, you might even be able to see a bright swath of stars arching overhead. That hazy band of light is the Milky Way galaxy. If you look closely, you can see dark patches in the Milky Way. Those dark patches are caused by interstellar dust blocking the light from more distant stars. What is not immediately apparent is that much of the space between the bright stars we see from Earth is actually filled with gas and dust. Astronomers call this gas and dust the interstellar medium, or ISM. While it might not seem very exciting at first, the ISM is what all of the stars we see form out of. Furthermore, this gas and dust produces some of the most spectacular astronomical images. This tour will show you a few of the most striking images available and explain a bit more about how astronomers can determine the structure and composition of the ISM by studying images taken of different wavelengths of light. Think of it as a guide to the top landmarks of the ISM. Throughout the tour, you will see text pop up when a complicated term or piece of jargon is used in the tour narration. Just click on the text and you will be redirected to an external webpage with a complete definition of that term. The tour is meant to be interactive, so you can really learn as much about the ISM as you want to. The first stop on our tour is IC 1396, an emission nebula located about 2,400 light-years from Earth in the constellation Cepheus. We are currently looking at an image from the Digitized Sky Survey. Let's switch to a higher quality optical image to get a better look at the structure of the nebula. The most striking feature of this emission nebula is its bright red coloring, which comes from hydrogen atoms within the nebula. Astronomers call this particular red visible light H-alpha emission. We only see H-alpha emission in regions where hydrogen is being ionized, meaning excited to the point of losing its only electron. Since we see H-alpha emission in IC 1396, we know that there is active star formation in this nebula, and that these new, hot stars are heating up the surrounding gas. One of these hot young stars is HD 206267, visible at the very center of the image. In fact, this is not just one star, but 3 hot stars orbiting each other in what is called a triple system. To the right of HD 206267 is a dark, sinuous globule called the Elephant's Trunk Nebula. The edge of this dark patch appears bright because it is being ionized by this young star. Astronomers believe that winds and radiation from HD 206267 are compressing the gas along the edge of the Elephant's Trunk Nebula and causing more young stars to form in a process termed triggered star formation. The difference between optical and longer wavelength observations is seen clearly by transitioning from our original optical view to an infrared image taken with the Spitzer Space Telescope. What appeared dark and opaque in the optical image now glows brightly in the infrared. This is because dust in this dense stellar nursery absorbs optical light, heats up, and then re-emits in the infrared. The different colors seen indicate different molecules present in the cloud. Green emission traces molecular hydrogen, while brown emission traces polycyclic aromatic hydrocarbons, or PAHs. These complex molecules are similar to what is found in car exhaust here on Earth. If we pan upwards in this image, we can see half a dozen newly formed protostars that are easily identified as the bright red objects within the cloud. These young stars were previously undetected at optical wavelengths because they are obscured by the thick cloud and dust surrounding them. Our next stop is NGC 2264, a region containing both the Cone Nebula and the Snowflake Cluster. This star-forming region is located about 2,500 light-years away in the constellation of Monoceros, the Unicorn. Once again, we will start by looking at a Spitzer image of the region. This image was created by combining several wavelengths of infrared light. Thus, different colors trace different components. For example, the green wisps indicate the presence of organic molecules mixed in with dust. The blue dots scattered throughout the image are older Milky Way stars. As in the Elephant's Trunk Nebula, newly formed protostars pop out at these longer wavelengths as pink and red specks cluster towards the center of the image. The stars seem to trace out the straight line spokes of a wheel or the pattern of a snowflake, leading to the name Snowflake Cluster. The fact that these stars lie along lines like this indicates their young age. Over time, the star-forming cloud will evolve and these young stars will move apart, breaking the current order. Panning further to the south, we can see the famous Cone Nebula pointing upwards towards the Snowflake Cluster. This pillar of gas and dust is 7 light-years in length. That's nearly twice the distance from the Earth to the nearest star. In this Hubble Space Telescope image, we are looking at just the top 2.5 light-years of the nebula. Over time, radiation from hot young stars formed in the region is slowly eroding away the nebula. These young stars produce ultraviolet radiation that heats the edge of the cloud. This high-energy, short-wavelength emission releases gas into the surrounding space. Further heating causes this hydrogen gas to glow red, producing the red halo seen in the image. For the final stop on this tour, we're going to be switching gears a little bit. Instead of looking at a region where young stars are forming, we're going to examine the remnant resulting from the death of an old star. Kepler's supernova was first observed on October 9, 1604, from northern Italy. Johannes Kepler, best known for discovering the laws of planetary motion, began observing the supernova on October 17th from Prague, and continued to track the object for an entire year. This supernova was easily visible to the naked eye and occurred within our own Milky Way galaxy. Today, astronomers can use modern telescopes to get a better look at the remains of this supernova. We can't see this remnant in our digitized sky survey image because the resolution just isn't good enough. So, let's start with an optical image taken with the Hubble Space Telescope. When a star explodes as a supernova, it is ripped apart and a spherical shockwave expands outwards at speeds of millions of miles per hour. At optical wavelengths, we can see where this shockwave, produced by the supernova, is slamming into the dense surrounding gas, producing bright clumps behind it. If we turn to an infrared image from Spitzer, we can see all of the tiny dust particles that have been swept up and heated by the shockwave. Finally, we can look at X-ray observations taken by the Chandra telescope. Low-energy X-rays are seen in an interior shell and trace the location of the material expelled by the exploding star. Higher-energy X-rays show regions of hotter gas. The hottest gas is located just behind the shock front in a region that coincides with both the optical and the infrared emission. A team of astronomers has combined all 4 of these images taken with each of NASA's great observatories to create a spectacular view of the complete structure of this supernova remnant. Well, that's all the ISM that we have time for right now. Hopefully this tour has given you a taste for just how complicated and beautiful the interstellar medium can be. If we truly want to understand how stars form, evolve, and die, we have to look at everything that is in between the stars, the stuff that those stars form out of in the first place. Finally, if your curiosity has been piqued by anything discussed here, make sure to check out the companion website to learn more.